Yes, it's always good to be drawing a picture of the situation. It helps us really to understand what all is going on with it, and then start labeling it with all the little details from the problem that we know about it. And then it becomes a bit more of a geometry problem. And then we can start just figuring out, okay, what's really going on in this situation? What sort of equations are going to be involved? In this particular case, our drawing is this two-dimensional drawing of a conical pile, which is being created out of sugar. Well, conical, of course, that means it's a cone. And this 4 cubic feet per hour that we have dumping into it there, that is telling us about a volume. So right now we know then we must be having to deal with an equation involving volume of a cone. So start by writing that formula out. And then we don't want to start by taking the derivative. Not yet, not in this case, because looking ahead, if I do that, I'm going to end up with both dr over dt and dh over dt in my final equation. I don't want that because I don't know both of those. In fact, I don't know either of those. Only one of those I'm trying to find. The question at hand here is how quickly is the height of the pile changing? That means that what this question is asking for is what is dh over dt, which means I somehow need to be able to get rid of this dr over dt. Doing that requires that I write a new equation for r that I then can substitute in for r up here in order to be able to get rid of it. And now in order to do that, I can use the information that's given to me over my picture here. Because you notice that I'm given r and h values here. So then I can write an equation then that relates r and h. So for instance, I might say that the ratio of the radius to the height equals 15 over 10. Because the radius is 15 and the height is 10. So now I can solve this equation for r. And by doing so, I know that r equals 1.5h, which I then can plug into my original equation up here on the top. So instead of r squared, it's going to be 1.5h squared. And again, I want to simplify that before I go and find my derivative. Otherwise, I have to be using product rule because the two h's multiplied together, and that'd just be a lot trickier. And when I multiply that 1/3 by the 1.5 squared, I end up getting 3/4. So it's going to be 3/4 pi times h cubed. And now I can finally take the derivative with respect to time. And from there, we can just plug in the values that we know for this particular situation. And finally, solve for dh over dt. And we end up getting an answer of about 0.006 feet per hour. Having now worked through this problem, what if we were, instead of being asked how quickly the height was changing, what if we were being asked how quickly the radius is changing? Like how far is this thing creeping out? How quickly is this pile creeping out and getting bigger as we look at it? So I also want to take a look at that situation. So it's the same basic situation, except now we're going to be taking a look at how fast the radius is changing. We're still going to start with the same volume formula though. And we'll still start by equating h and r in an equation. The only difference is that this time, instead of solving for r, we're going to solve this for h. That way we can plug it in for h in the other equation and get rid of h in this equation over here. And so when I solve that through, I find that h equals 2/3 r. And so I'm now going to take what h equals, and I'm going to plug that in for h up here in this equation. And then, as usual, I would like to clean that up a little bit before I go much further. And so now notice that we have an equation that's written entirely in terms of v and r. So now I can worry about going ahead and taking the derivative with respect to time. And now that we have that derivative, we can go ahead and plug in the values that we know in this case. And then we can solve for dr over dt from there. And then that gives us a rate of about 0.008 feet per hour at which the radius of this pile is increasing. And then that's done.